So today I'm going to be covering joints and folds. And fair warning, I have lots of pictures here because there are so many fantastic landscapes out there that are a result of jointing in bedrock and of folding. So let's talk about joints first. Joints are, and no, not that kind, cracks in rocks with no movement, where there's been no movement. Remember to distinguish a joint from a fault. A fault is a crack in the Earth's crust where there has been displacement. Joints are just breaks in the Earth's crust, and these are weak zones in the rocks. And these weak zones can take on different characteristics, and they weather. The Mother Nature concentrates her weathering efforts in these weak areas, and from weathering and erosion, we can get some really, really fantastic landforms out there, all as a result of the inherent weaknesses that rocks have. So we talked about this earlier. This is how granite typically weathers. Remember, granite is formed deep underground under great pressure. When it makes it up to the surface, it will expand along these natural weaknesses in the rock. So we get this peeling effect of the granite. We say that it exfoliates. Go to Joshua Tree. You see all sorts of granite boulders that have this spheroidal, this rounded shape to them. That, remember, is Stone Mountain in Georgia. Then again, you saw this before, but just to refresh your memory, look how it's peeling like an onion. So when the top slabs are released, that releases pressure on the bottom slabs. So they will tend to expand, and then over time, they will peel away. Again, that's what makes climbing dangerous in these in situations like this, because we don't know when these layers are going to drop. Then basalt is another one, another rock that we have lots of here in California. And under certain conditions, when the lava cools, basalt will have these weak areas in it that will have these polygonal shapes to them. And that's where weathering and erosion is going to be concentrated. So we end up with these beautiful angular columns that form. And that's Devil's Postpile here in California. And you see the top part. Look at these. This is what I mean by these polygonal weaknesses. Mother Nature's pavestone here. Those ended up being sheared off, smoothed off when a glacier moved through that valley. So that's why the tops of the posts are so smooth. Then Devil's Tower in Wyoming is another example of columnar jointing. There are just some really fantastic landscapes out there, and famous landscapes too, that are the result of columnar jointing. These are just different views of Devil's Tower. Sticks out like a sore thumb. It soars about 900 feet above relatively flat land. It is located in the northeastern part of Wyoming. There's some more. You see the talus. So this is weathering in action here, physical weathering in action, where big pieces of rock become smaller pieces of rock, and we have a talus slope that's building up at the bottom. Climbers like this area too. I was out there a couple of summers ago, and there were people climbing up the columns. When we walked around the back side of it, and there were some of the climbers coming down, and I asked them what it looked like at the top. And I think one of the climbers was from France, so I couldn't really understand him, but he said it looked metallic up at the top. Well, that was probably just the sun shining on it and the gray color of the columns. There's another view of it, so you can see just how obvious it is. And then Giant's Causeway in Ireland is also columnar basalt. This legend has it that this is the road that one of the major mythic figures in Irish folklore, Finn McCool, he used this road to go to his home at the bottom of the ocean. Maybe it was Aquaman. And then this is Monument Valley in Utah. You see lots of commercials filmed here, along with Alabama Hills on the east side of the Sierra Nevada. But this is sandstone. Alabama Hills ends up being granite, and it erodes in, the granite erodes in this spheroidal manner. But sandstone is like limestone. It has these angular jointing patterns in it. So that's where weathering is concentrated then, in those angular patterns. Think about this. What you're seeing are just remnants of this huge amount of sandstone, just layer after layer after layer after layer of sandstone that was here, and it weathered differently. Even though this is all sandstone, some sandstone is more compact than other sandstone, so some of it is less resistant to erosion, so it's weathered away. What you're seeing here is the more resistant layers of the sandstone. So you have plateaus, you have monuments, you have buttes, you have pinnacles, you have spires. It's just an amazing place. If you ever are in that part of Utah, you have to stop and see this. It's Navajo land. The Navajo have built a hotel that is in this area up here. So every room has a view out on the monuments. And when at sunset and sunrise, the colors are just phenomenal. So what you're looking at here is sand. Eventually, all these will be eroded away, but for now, because of those jointing patterns, we have this lovely, lovely, lovely place in the U.S. that we can go visit. These two are called the Mittens, and you can see why that would be. Or I guess they could be called teapots too, but they refer to them as the Mittens because there are two of them. There's another view. I told you I'm going to have a lot of pictures here. And this is on the way into Monument Valley. Just some beautiful sandstone structures. This is not quite in Monument Valley, but very nearby. And I chose this picture because I wanted you to see those jointing patterns here. See how they're almost at right angles to each other. And look at these little pieces, these tiny little pieces that are left behind. So almost like a tablet. And then the other thing that sandstone is capable of doing is forming arches. You know, there's Arches National Park in Utah. Arch after arch after arch, it's all in sandstone. This happens to be another area. This was a valley, a dry valley, and I guess when it's wet, there's water running through it. But the Native Americans used these as their dwellings. You can see where you would have protection from the elements. Pretty cool. And it's like a whole row of them down this valley. Here's some more of them, same area. So those are arches in sandstone, again related to the jointing pattern. I threw that one in there in case anybody's interested in exfoliation in granite in Texas. This is Joshua Tree. And again, you see this is granite, and you see the spheroidal weathering. It looks a little bit different than what we saw in Georgia or what we see in Yosemite, but that's because this is a desert area. So a dry climate, the weathering will look a little bit different. The features will look a little bit different, but we have the same typical exfoliation taking place. And this is a house. If you notice it up here, this crazy gate right here. Many years ago, we were traveling into Joshua Tree, and as you're driving through to get to Joshua Tree National Park, you are come to a little town called Joshua Tree. And on both sides of the road into Joshua Tree, there are just all these granite boulders at the tops of the mountains. So I wanted to get closer and get a picture, and we took this road and it dead ended. So I got out to get a picture and realized that there was this rusty, spiky gate in front of me. And then I looked up even further and I saw this crazy, beautiful house. Whoever designed this, and after the fact I learned who had designed it, had this blend in with the landscape because you have these exfoliation layers. Look at the roof line of this structure. Just totally in balance with Mother Nature here. So later on, I realized that this was a very special house. Well, I knew it at the time, but later on realized even more so. So let me show you some pictures of it. Look at it. That's where it is. It's tucked in to those granite boulders, and you see the rounded shapes of the boulders. And there's another view of it. Looks out over, it's close to the Joshua Tree National Park. So it looks out over that park. Everything is meant to blend in with the landscape around it. Look at the inside here. It's stone and concrete and wood. Just gorgeous. Moving my dream home. Look at that. They've decorated with some of those granite boulders. So this was designed by a famous architect from San Diego by the name of Kellogg Bangs, B-A-N-G-S. All right, that brings us to folds. Folds are bends or warps that form in rocks subjected to compressive forces at depth. Remember what the behavior of the rock is here. It's going to be ductile. So when they are compressed, and again, it's usually a long period of time where the rocks have been subjected to these stresses, but they're malleable. So these warps that show up in the rocks have names. If it's an up warp, it's an anticline. If it's a down warp, it's a syncline. A monocline is like a step-like fold. So there are all sorts of derivatives of these. I won't bore you to death with all of them. I just want you, as you're driving the highways and byways of the world, look for these things. The ridge and valley where I'm from in the Appalachian Mountain is there because of folding. So a little bit of terminology for folds. The layers of rock that go into the steepest point of the fold are called the limbs of the fold. And you notice that, remember our rock code, we have all kinds of different rock layers that have been warped at depth. So here is an anticline. That's what we call the fold shaped like an arch. So A for arch. And then a syncline is the down warp. The steepest point of curvature in an anticline or a syncline is called the axis of the anticline or the hinge line of the anticline or syncline. If the hinge line dips, we call that plunging. Now, everything isn't up and down straight because Mother Nature is messy, as I've said time and time again. So the hinge line can go off at all sorts of different angles. So when it does plunge back into the earth like that, it's called a plunging fold. So think about this. These form at depth, but now we can see them in road cuts. And it's because of tectonic forces at work. When Pangea formed, you had the continents, the plates that were crashing into each other, and these rocks that were flat lying to begin with, they were uniform, they were just horizontal, they folded up at depth. Remember, these are at depth inside the earth, so they folded up, and now through tectonic uplift, through weathering and erosion, they're at the surface. Everything that was on top of them weathered away. This is a monocline, so just kind of like a step, you know, kind of a gentle fold. Then here's a syncline, here's our anticline, here's an asymmetric anticline. And then if those compressive forces are happening when these rocks end up getting higher up into the crust where the rocks are more brittle, and there's still compressive forces that are strong enough to cause breakage, we'll have a fault. So these are faults that have folds, that have actually been faulted. And then this is in Maryland, a portion of an interstate. I don't remember what the number is right now. It goes directly through it's cut through the ridge and valley. So that is a syncline, and you see all the different types of rocks that have weathered here. All of them weathered differently. There's a little bit of coal in here, there's some limestone, there's some sandstone, there's shale in here. But again, these form from compressive stresses that are acting over very long periods of time, and the rocks have to be ductile. Here's an anticline. You see the arch-like shape to it. And then here is a syncline that is really, really folded. This is one of those chevron folds, the V shape. This one is kind of open, so the force was even more powerful here. Here is an anticline that has that V shape to it. So the stresses were more powerful coming from this direction. And that is a monocline. These are overturned folds. This is in Pennsylvania. These are overturned folds. Here are the limbs. You see the limbs are almost horizontal. If we could see one of them down here, it would be coming this way. See a limb that's horizontal here. And then this is what it looks like from space. This is false color imagery, where green shows up as red. A lot of people that use these for looking at different forests, looking at the health of forests, the red color shows more distinctions than just the green forest would. But you see these weird zigzaggy shapes, and it's kind of hard to understand how the structure underneath of these folds can give us a landscape that looks like this kind of thing. Well, again, think about different rocks weathering at different rates. Some rocks are going to be stronger than other rocks. So the rocks that are making these ridges here, and the ridges are where we have most of the vegetative cover. Down here we have urban areas, agricultural areas. Those are sandstone. Sandstone is more resistant to erosion than either shale or the limestone would be, and that's what the valleys are composed of. And you can see here the sandstone, here's the layer, these different layers here. I keep saying here. Hopefully you're looking at what I'm pointing to. The different layers, and where these ridges are, that's the more resistant bedrock. Where the least resistant bedrock is to erosion, that's where the valleys have formed. So ridge and valleys, all of these features up here, the ones that you see are the ridges. These green areas in between are the valleys. Folded rocks. Map of the US. I've circled 2 locations. This is the basin and range here. Faulted mountains, fault block mountains. This is the ridge and valley. Over here in the east, folded mountains. 2 different structures. Yes, we get mountains and we get low areas in between the mountains, but they're formed from totally different structures. Normal faults over here in our basin and range, folded mountains over here. And that's the ridge and valley area. I've got some better pictures of that in a minute, but let me get back to this. I want you to pay attention because I'm going to go a little bit more into detail. Since this is my home territory over here, I'm going to go a little bit more into detail about how all this formed. I lived in Virginia, over in this part of Virginia, but we have a coastal plain that is a geologic region. We have the Piedmont, which is a geologic region. We have the Blue Ridge, which is a geologic region. We have the Ridge and Valley, and we have Plateau area. That is all a result of what happened when we had these microcontinents, these island arcs that were out here crashing in, the Eurasian plate crashing into North America plate to form Pangea. This is all a result of that. And I'll talk a little bit more about that, but I wanted you to pay attention to where we're looking at right now. So I'm going to go a little bit more into detail about those. Okay, this is pretty special. These are folds that you see in the rock. We know that those happen at depth. But what about these breaks? See the offsets? There's the mark of Zorro. What kind of fault is it? I'll wait up for a few seconds. 1, 2, 3, 4, 5. And if you said reverse, you are correct. A reverse fault is where the hanging wall has been pushed up over the footwall. So find the break. Break is easy to see. It's right here. So the hanging wall is above the break. What did that hanging wall do? It moved up. So these are thrust faults. Again, they will form where these compressional forces are at work in brittle rocks. So these rocks have to get higher up toward the surface before those compressive forces will actually break them. So they were malleable at depth, and that's where the folds come from, but the faults come from the movement of these upward. These are plunging anticlines and plunging synclines. We use the rule of V's here. A V that opens in the direction of the plunge is a syncline, down here, while one that closes in the direction of the plunge is an anticline. So these are all anticlines, plunging anticlines. That's it in cartoon form. Let's look at what these look like in real life. This is a famous structure in the West. This is called Sheep Mountain. Move my, you all can't see this, but I'm seeing it. I need to move it. Sheep Mountain in Wyoming. These are all different types of rocks that have been folded. You see that this pinky sandstone here matches these layers of rocks over here. We talked about hogbacks before. These are hogbacks. Then you see this erodible layer right here, this reddish color where there's not a lot of rock left to it. It looks like it's more rubble than anything else. So structural geologists will map these and they'll start reconstructing what these look like. So these rocks match these rocks over here. These rocks match the, whoops, I went too far, match these rocks. That is an eroded anticline. These rocks match these rocks. They look like overturned canoes. And here, and I call these snouts. I don't know if I'm the only person that does call it that, but the snout of the anticline, here's another snout right here. These rocks match these rocks. These rocks match these rocks. These rocks match these rocks. So the whole thing, here I am with my stupid pens again, would have been like that. But got to the surface, and again, the more resistant rocks are the ones that are sticking around like this. The others are the ones that have been eroded down where we're seeing kind of a level area, not a lot of relief to those. All right, what about basins and domes? Basins and domes can look an awful lot alike, especially if they're really eroded. These examples right here are going to be helpful because we're seeing that the rocks haven't all been eroded down to base level. So how do you tell the difference? Because if you're out there hiking, you would be going up a ridge, down a ridge, into a little valley, up a ridge, down a ridge, into a valley, up a ridge, down a ridge, into a valley, and you'd be doing the same thing over here. But these are different structures. The structure is different. If you look at the structure here, this is an anticline. This is a syncline. Well, if you have a handy-dandy geologic map with you and you look at the age of the rocks, what you will see is the youngest rocks are in the middle of a basin. That's where the younger rocks are. The older rocks are on the bottom. As we get higher up, the layers get older. Scratch that, get younger. So the younger rocks are going to be in the middle of a basin. So if the younger rocks are in the middle of a basin, we know that is a syncline. Also, if we're standing in the middle of this, those rocks are going to be tilted toward us. Do you see that? So they would be tilted this way, tilted toward you. That is a syncline. In a dome, the oldest rocks are in the middle of the dome. See what's happened here? You have erosion that's taken place, and the older rocks are getting exposed in the middle of the dome. So if you have your geology map and the oldest rocks are in the center, then that's a dome. But if you don't have a geology map, look at how the rocks are oriented, the dip of the rocks are oriented. If you're standing here, then those rocks are dipping away from you. And if that's the case, that is a dome, and the structure underneath is an anticline. This is the Sinclair Dome in Wyoming. This is a very famous dome because it was one of the first big gas and oil strikes in America. And notice these rocks. These rocks are matching these rocks over here. These rocks match these rocks. These rocks match these rocks, but they've eroded now. Here are some more of those hogbacks. So the more resistant rocks will stick around. These lower areas are where the rocks weren't as resistant to erosion. And that is another dome. I told you there were going to be a lot of these pictures. But this is easy to see in the West. This is why most geology schools in the East, they have their field camps in the West, because you don't have a lot of soil on top of the rocks. You don't have a lot of vegetation. You don't have a lot of forested areas that are covering up the structure. It's right there in your face. And you can see all these different rock layers and how they or over time making a structure. This is a warped dome, making a structure like this, an anticline. And this is back where I grew up. This little feature right here, there it is on a satellite image right there, has just baffled more people, especially people that don't know anything about geology. I heard all my life that this was a volcanic crater. That was one idea. Then people say, no, it's an old lake bed. Then they would say, no, it's a crater, a volcanic crater, not a volcanic crater, a crater where a meteorite has hit. So all sorts of things. It's none of those. Those sound pretty exotic, but it's none of those things. It's an eroded anticline. There was limestone in here, and if you remember the structure of limestone, it's got that brick-like pattern. So at the point of steepest curvature, there are going to be cracks in the rock, and where's water going to go? Into those cracks, and it seeps into the limestone. Let me see if I can make a brick-like pattern here, because that's what our limestone is showing. This is terrible. I'm sorry. So the water gets in, and the limestone got eroded away. It disappears. Well, what happens here to this rock? It collapses. Gone. So pretend that part isn't there anymore. And that is an eroded anticline. This, again, is this massive road cut. And here, again, is something to keep in mind. When we think of synclines, we think, okay, it's a down warp, so maybe they should form basins all the time. Well, no. It just depends on how strong the rocks are once they make it up to the surface. Are they more resistant to erosion, as these are here? Because look, we have this down warp here, these down warped rocks, but look what they're making. They're forming one of those ridges. Aha. Here's an anticline. Some of the limbs are gone over here. They've weathered away. And this is a monicline, again in the west. This is in Utah. This always reminds me of a marble cake. All these different colors that look like they're swirled around as a result of the differential erosion of the rocks. So all these, that was an anticline, but the tops of the anticline have been weathered away, leaving these remnant rocks here. So what's the significance of folds? Well, the geologic significance is that the symmetry of the fold will give a clue as to the type of stress and the direction of stresses. The amplitude or the height of the fold we look at, that can also give us a clue as to how powerful the forces were. And then we look in the direction that the limbs point. That gives us this clue as to the direction that the forces were coming from. And the other geologic significance of folds is that they make really good traps for oil and gas. And that is where I'll stop this time. We'll pick up with how that happens next time. Talk to you later. Bye-bye.